Okay, part two. We're continuing here talking about the evolution of stars. What happens to stars as they go through the journey of their lives? We talked about the sun, which recapped the sun is a main sequence star. It started as a protostar, then it started fusion. Now it's a main sequence star. It's going to hang out there for a long time. It's going to run out of hydrogen, start to collapse. Then the helium that's built up in its core will all fuse together into carbon, which makes the whole star expand and it becomes a red giant for a while. That's burning helium into carbon, starts to collapse again, not hot enough to fuse the carbon. You're just left with a ball of carbon. The outer layers kind of wisp away over a long, long time, and you got yourself a white dwarf and a planetary nebula. Okay, well, what about bigger stars? There are stars that are big enough that you can fuse the carbon. That ball of carbon that would become a white dwarf in a smaller star, it gets hot enough for the carbon to fuse to other carbon. And more and more and more fusions happen. So many fusions happen. And you can create elements as big as iron here. That maybe rings a bell. You might hopefully be thinking about our good old binding energy per nucleon graph, which told us that iron is the most kind of stable in a binding energy sense here, because at the top of the binding energy per nucleon curve, it would cost energy. This is like where it starts being the case. It would cost energy to fuse irons into heavier stuff because you would, end up kind of going downhill on this graph. Your binding energy would decrease. That would make more mass. You got to put in energy to make that happen. All right, so this is all the stuff that can fuse naturally in a star, in the core of a star. And we fuse all of the elements up to iron get fused in the center of a star. All right, and just an idea of what this kind of looks like, you can have a supergiant star, especially once it's in this stage. The core is teeny tiny compared to the star, but you have all these different shells, and like a lot of this fusion is all kind of happening at once. So you might have hydrogen, helium fusing into helium, and helium fusing into carbon, and so on, so on, so on. And you end up, it all kind of sinks to the bottom, and you get this iron core. And it's always an iron core. That's like the, furthest you can go. Because again, that's the top of the binding energy per nucleon curve. Okay, then what happens? Well, the high mass stars are more exciting because they have enough mass to fuse carbon, and they also have enough mass that when you get your little ball of iron now at the end, it's being compressed by so much mass that the math kind of says the force is big enough for those electrons to basically be right on top of each other. You're overcoming this electron degeneracy pressure, which remembers the pressure keeping like a white dwarf from collapsing. Well, the amount of mass is so much it overcomes that pressure. It's like trying to force the electrons right on top of each other, and they go, no, I can't. It's not allowed. It's illegal. And so what they do instead is the electrons essentially dive into the nucleus of the atom. The whole atom collapses. The electrons and protons all sort of smash together. You end up with a ball of neutrons, and the collapsing of those atoms, like in a split second, the amount of energy that released is gigantic. It's a huge explosion that we call a supernova. So this is what a supernova is. It is the death of a giant star, a really big star, where the atoms are really collapsing on themselves. Tons of energy comes out in the process, and all the outer layers of the star get like dramatically blown away then by this big explosion. And they send that gas flying through space at, significant fractions of the speed of light sometimes. Also, this is a huge source of energy. And remember, we said you can't really, like, iron's not going to naturally fuse to iron by itself. You would have to put in a ton of energy to make that happen. Well, here's a ton of energy right on a big soup of a mush of all these heavy atoms. And what happens is the energy from the supernova is enough to fuse these elements into heavier elements, all the way up to uranium. So everything bigger than iron, this is where it comes from. Okay. And truly, in the universe, this is where all elements heavier than iron come from. You got yourself, a piece of gold jewelry laying around, or a piece of silver, or heck, take out a penny. Um, all of that stuff came from a dying star that exploded and spit out those elements and scattered them through space. And, that little cloud might have collapsed and formed another star, which cooked up some more elements and exploded and spread them through space. And eventually, we get a cloud of gas that condenses and forms a star and forms some other little rocks around it. And we're on that third rock on Earth. Yeah, so our planet, our solar system was formed by elements of previous generations of stars. So we have all kinds of heavy elements around here. Yeah, really everything beyond lithium comes from stars one way or another. So all the carbon in your body was at one point in time fused at the center of a star. That's where carbon comes from. So it is true, you are made of star stuff. So that's the role of supernova. They spread these heavy elements, they cook them up, spread them through the universe, and we get new and new generations of stars and planets and star systems. Here's some fun supernova pictures for you. They look like big explosions. That's what they are. And fun fact, they are super bright, ridiculously bright. Okay, here's like a nearby galaxy. And that's a galaxy. A galaxy, for the record, is hundreds of billions of stars, give or take. Okay, so the sun is one star. The solar system is one little measly star system. And just even getting to like the next planet is a huge ordeal for us. Well, imagine 100 billion stars all in one big disk, which is impossible to imagine. It's a crazy number, but that's what a galaxy is. All right, billions and billions of stars. And what this is a picture of, that's like many billions of stars, and how bright they are. That's a supernova. That's one star exploding. The brightness can rival the brightness of a whole galaxy of stars. It's incredible the amount of energy that comes off here. Okay, so how do we, decide where these cutoffs are? Well, we have some cutoffs. And these are some limits that you want to know that they will sometimes ask you about. This is really what determines what's going to happen to a star. It's all about the remnant, is what we say. The stellar remnant is usually how we're going to talk about these, which means the leftover core, the core that's left over after fusion. All right, so if the core, the leftover remnant, is 1.4 solar masses or less, you're going to end up with a white dwarf. That's the limit where any heavier, you got enough mass to overcome that electron degeneracy pressure. Okay, and so this one we call the Chandrasekhar limit. That is the maximum limit of a white dwarf, 1.4 times the mass of the sun. If you're above that Chandrasekhar limit and you have enough mass to overcome electron degeneracy pressure, the next thing you can get is called a neutron star. Again, you've collapsed the atoms. The electrons fell into the nucleus, combined with protons to make neutrons, more or less. And you end up with a ball of neutrons. This is as dense as the nucleus of an atom. This is as dense as stuff can really be. Okay, it's this crazy thing where if you took a teaspoon of a neutron star, whatever that even means, because you couldn't really do it, but if you had a teaspoon full of neutron star stuff and you just turned it over, that ball of stuff would burrow its way through the center of the Earth. It is so dense and heavy. But there is a limit for this too. There is neutron degeneracy pressure that keeps the neutrons from being on top of other neutrons, because that's also illegal, says quantum physics. But there is enough pressure, enough mass that you could have to overcome even that pressure. And this is called the Oppenheimer-Volkoff limit. This is 3 solar masses about. Both of these are very rough numbers. We're still honestly kind of working on these. But these are usually the numbers you'll see, and the IB will give you numbers in this kind of ballpark. All right, so if the core is more than 1.4 times the mass of the sun, it can become a neutron star. And if it's more than 3 times the mass of the sun, even that is overcome. And this is how you get yourself a black hole. All right, so you overcome neutron degeneracy pressure. All the neutrons get pushed on top of the neutrons, and all of the mass of the core collapses into question mark, a singularity. A single point, possibly, probably, a very incredibly, infinitely small point where all of the matter of that star, the core, we should say, the remnant, is in one spot. Really, math-wise, like a point. Black holes are crazy. There's a little info we can kind of get into about black holes. But we call them black holes because the gravity is so strong around a black hole, light cannot even escape it. All right, the rules of relativity say light has momentum and stuff. Light can be bent by gravity. And if you're hanging out near a black hole, you're trying to send out an SOS signal, nobody's going to get it because light speed isn't fast enough to escape. All right, so that's why they're black. There's no color because any light that's coming off of them doesn't make it away from the star. Its gravity is so big. All right, and we call that a singularity sometimes because, again, the idea is all the neutrons collapse to a single point. One thing to know about black holes is it is not like infinite mass. It is maybe 3 times the mass of the sun, just in a point smaller than the tip of your pencil, which makes it a black hole. Okay, here's a recap of what you want to know. This is the common type of thing they ask you about, is to like identify what's going to happen to a star based on its mass. And you got 3 different paths. You got the low mass path that the sun is going to take. A so-called average star turns into a red giant, and you're left with a planetary nebula and a white dwarf. Bigger stars will turn into supergiants. They will go supernova, and you're left with either a neutron star or a black hole. You want to be able to talk about these limits to justify. So if they're like, the remnant is 2 times the mass of the sun, what happens? And you go, oh, well, that remnant is above the Chandrasekhar limit and below the Oppenheimer-Volkoff limit, so it's going to be a neutron star. Big enough to smush the electrons together, not big enough to smush the neutrons together. All right, that's kind of the thing. Just for a very ballpark idea, here's like some sort of initial mass numbers, because the idea is like the remnant, most of the stuff is not in the core. So the remnant is much smaller than the actual mass of the star, like on the main sequence. So this is like even rougher than these numbers, but if a star is, say, 15 times the mass of the sun or bigger, it's a good bet that its core is going to be at least 3 times the mass of the sun, which means it's a good bet that's going to be a black hole. That's sort of the idea. But these are super rough, just to give you a very ballpark idea of where things will end up. But there you go. That's the evolution of stars that you need to know about. Have fun.